Our next speaker is Stephen Strogatz, the Winokur, Distinguished Professor for the Public Understanding of Science and Mathematics at Cornell University. He received his undergraduate degree from Princeton, was a Marshall Scholar at Trinity College in Cambridge, and received his PhD in applied mathematics from Harvard. A serious mathematician, he is also a prolific podcaster and author of books that help the public appreciate the beauty and ubiquity of mathematics. He looks at physics, biology, and social science through a mathematical prism, studying phenomena as diverse as the human sleep-wake cycle, the geometry of supercoiled DNA, crickets chirping in unison, and swarms of flashing fireflies. Elected to Class 3's section on Applied Physical Sciences, Dr. Strogatz's title is Getting in Sync, the Math and Science of Synchronization.
Thank you. All right, hi everybody, and thank you very much for this great honor of having a chance to speak to you all. Well, actually, Dr. Darwin's remarks hit me pretty hard because my parents also put the arm on me to be pre-med for a while. And, I always loved math. I liked all of school, in fact. And I took biology in high school, and I was so bored with it that I begged the teacher to let me drop out. And she said, okay, but you have to promise to take it in college. And I thought to myself, I can promise that. And I did, but I didn't intend to. Anyway, then I had a brother my older brother, 12 years older, was a lawyer. And he said, Stephen, what are you really going to do with math? Like, why don't you take these pre-med courses in college? That would be much more convenient than taking them later. And you might actually like the science. You don't have to be a doctor. Like you like chemistry, you like biology, maybe, if you did it at the right level. Why don't you just take it? So I thought that was a persuasive argument, and I found myself as an undergrad at Princeton in John Bonner's biology class for freshmen. As a junior, I switched in my junior year to pre-med. And I was taking freshman chemistry, freshman biology, and organic chemistry all at the same time. 3 labs a week, not good for someone like me. But anyway, it turns out that this biology course was really interesting, especially when we got to DNA and the double helix. I could see the connections to my math courses, how geometry would tell you something about how base pairing would work and how the molecule would replicate. So I got all fired up about the ideas of combining geometry and biology. And so that leads me to the part where we talk about our personal journey. Somebody else was thinking of combining geometry and biology. This gentleman, Arthur T. Winfrey, wrote a book. When I was in England on this Marshall Scholarship, I was taking a very traditional math and physics style applied math course, and I was getting a little bit bored, having done this senior thesis back at Princeton about geometry of supercoiled DNA. So I was really all excited when I saw Winfrey's book in Heffer's bookstore across the street from Trinity College, Geometry of Biological Time. There's some other insane person who thinks that geometry and biology can speak to each other. Except he was bringing in time, and I didn't really understand why. So I found myself looking at this book, and inside the book it was clear that it was written by a very strange person. He had data from his mother's menstrual cycle. And what you see is you see this big graph of, why? His mother was using the rhythm method, to try to deal with her reproductive status, let's say. And you see all these interesting data points showing the time intervals between her periods, and then occasionally interrupted by 3 initials, which are his brother, and then his sister, and so on. So anyway, he had all this really nice data from his mother, but I came away thinking, this guy's really kind of strange, and I put the book back, except then a few days later I found myself wanting to look at it again, And I came back to the bookstore and I read more of it, and I thought, let's see if he's for real. So I started looking in the bibliography, and he's got papers in Science, he's got papers in Nature, and he's just a phenomenally creative scientist. So I asked Art Winfrey, could I work with him over the summer? And that changed my life. So Art Winfrey was my mentor. I mean, of course, like all of us, we have many mentors to thank and get teary-eyed about. I'll start choking up if I go on about this. I think I better stop. But anyway, in learning from Art about how all the things that math could have to say about biological rhythms, that's the time part of geometry of biological time. That if we look at not just his mother's menstrual cycle, but circadian clocks, glycolysis in yeast can sometimes show oscillations. There's just a lot of different rhythms, heart rhythms, pacemaker neurons. There's a lot of rhythm keeping in biology. And so much of my life has been about the math that can inform, can maybe help answer some questions that biologists aren't trained to answer with their tools. So I want to jump into a few examples of systems that synchronize themselves. In case you haven't seen this sort of thing before, here's a good example. This one's kind of spooky if you've never seen it. This is not living creatures. This is just inanimate metronomes of the type that a musician would have, you know, to keep time. What you're going to see in this YouTube video is this gentleman has 5 metronomes. And also notice that there are 2 soda cans on their side. Those are going to act as rollers. They're empty. He's going to first start the metronomes ticking, and he's going to just keep them on the tabletop, and they won't get in sync, and you'll be able to hear that they're not in sync. But then when he's going to lift the board up and put them on the rollers, and just through the, well, I'll just let you watch what happens. You'll see. Isn't that amazing? I noticed some audience reaction. At first you thought they were in sync, right? There was a little gasp in the audience. That often happens, but what was happening is one of the metronomes was not quite cooperative. You may know some from faculty meetings. May have encountered some of these that don't quite match into consensus. But that one eventually got swayed, and then they were all spontaneously synchronized. So that's an example of, just in this case, through Newton's laws, and I mean, from purely mechanical forces, systems can come into sync on their own. And it's kind of spooky. It's like a naive understanding of thermodynamics would lead you to think, that's not what I was taught. I thought systems go to ever greater entropy. Aren't they supposed to go to disorder? This thing is spontaneously ordering itself. How does that work? Okay. So now, in case you wonder, well, that's kind of a silly example. Who cares about metronomes on a board? Here's a real-world example that is reminiscent of it, except that the metronomes are going to be pedestrians. They are people walking across London's Millennium Bridge on its opening day. So it's June 10th. It's a big, happy occasion. It's the first new river crossing across the Thames, footbridge across the Thames in 100 years, to celebrate, of course, the millennium. And Queen Elizabeth is there, as you can see, and something like 80,000 people came out that day for this wonderful, and probably a lot of you have been to London and have walked across the Millennium Bridge. It's a beautiful footbridge. Lord Norman Foster, who designed it, said he wanted to give London a blade of light across the Thames. It's a very thin, ribbon-like structure. It's not a traditional suspension bridge with big, droopy cables overhead. Instead, it's got suspension cables that are, it's like if you took a guitar string and stretched it taut across the river. It's what's holding up the bridge, these suspension cables that are stretched tight like rubber bands. Now, something funny and unexpected, unknown to civil engineering, happened on opening day, which is that when the police let the pedestrians stream onto the bridge, very quickly the bridge started to wobble sideways. Now, okay, if you're thinking about the old thing, oh yes, I've heard about this with soldiers marching across a bridge, they have to break steps so they don't resonate with the vertical motion of the bridge. That's not this. This bridge did not move up and down. This bridge moved sideways. All right, so watch. This is from a BBC show called Science Shack.
The most dramatic and shocking footage shows whole sections of the crowd, hundreds of people, apparently rocking from side to side in unison, not only with each other, but with the bridge. This synchronized movement seemed to be driving the bridge. But how could the crowd become synchronized?
Exactly. How could the crowd become synchronized? What was causing the spontaneous synchronization of the pedestrians on the Millennium Bridge? By the way, they had to then close the bridge. They put in dampers underneath to make it, so that it wouldn't do this anymore. So it will not wobble anymore, I'm afraid. I think it would have been a fantastic like a really great tourist attraction. But of course, it could be dangerous if the bridge were to break. That's not good, or people get hurt. So no one got hurt that day. But it was a great embarrassment. Except that science didn't know about this thing. I mean, civil engineering of structures that interact with human beings, especially in crowds, is a continuing puzzle in that branch of engineering. Okay, so now let me keep moving here. I want to talk about self-synchronization in biology. There's all sorts of instances, not just the pedestrians on the bridge, but as Nancy mentioned, fireflies in some parts of the world spontaneously synchronize. It's just the males will get in sync in their flashing. Here's a little image of cortical and thalamic neurons. You can see them flashing in sync. They've been treated with voltage-sensitive dye so that they will light up when they fire. And our hearts, in the sinoatrial node of your heart, you've got 10,000 cells that are firing in unison for billions of beats in your lifetime on their own. Now, so that's what I want to quickly go through here with you, is a simple model of this sinoatrial node that National Academy member Charlie Peskin worked on a long time ago, where he made an extremely simplified model. The real heart cell, you'd have to describe hundreds of ionic currents, and I mean, we're not going to do that. Peskin's model, in the spirit of applied math, is let's try to understand the simplest problem that we don't currently understand. In other words, why do the real problem when you can be confused by something much simpler instead? So, because it is really a tricky problem. So he's got this variable x that is sort of like a voltage, if you want to think of it that way, and it's going to build up on this curve, sort of like an RC circuit charging up, a capacitor charging up. So you build up in this concave down fashion, and then when you hit that top, that threshold at 1, the cell is going to fire and instantly discharge and then instantly reset to 0 and start charging up again. And so that will make a so-called relaxation oscillator. And so that's his little model of a single pacemaker cell. And then he imagines, what happens if I have 2 of these pacemaker cells? Can I show that they'll always get in sync if they obey a certain simple rule? So his rule is, you can see there's cell A is down at 0. It has just fired. Cell B is somewhere else in its charging cycle. And so then time proceeds, and they both move along this charging curve. He's going to suppose they're identical, just for simplicity. And then when B reaches threshold in the middle panel, it's going to fire. And when it does fire, then you see panel C, the third panel, you see the oscillator, or the cell that was, cell, that one A, has gotten kicked up. So here's Peskin's idea, that when one cell fires, it kicks the other cell up by some amount, epsilon, towards its threshold, or it kicks it, if that causes it to go over threshold, then that cell will fire too. And that's it, that's the whole model. You're either kicked up by epsilon or over threshold when someone else fires. And the question was, what if I have a big population of 10,000 of these? Will this thing automatically always get itself perfectly into sync? Is that rule sufficient or not? And it's a hard math problem because of these jumps. You know, if you took calculus, you learned you're supposed to study smooth functions or continuous functions, but I just described 2 kinds of jumps, where someone fires off a pulse and then you're instantly resetting to 0. Those kind of discontinuities make the math nasty. And so I had read about this in Art Winfrey's book, Geometry of Biological Time, that it was an open problem to really figure it out. And so with my friend René Marollo, we worked on this problem. So what Peskin had conjectured is that this system would always get itself in sync. As he put it, for arbitrary initial conditions, it will always approach a state in which all the oscillators fire synchronously. And so I ran a little computer simulation of that, where what you're seeing here is, as a function of time, I've just divided time into 10 bins per period, and I'm just counting how many oscillators out of 100 are firing in each of those 10 bins. And at first, if you see the histogram looks sort of flat, it would be like you would hear there's somebody firing all the time. But then eventually, like around 9 or 10 periods in, you see a big spike emerging. That's all the oscillators going off at the same time, sort of like the metronomes were doing in that little demo. So the computer suggested that Peskin's conjecture was right, and then Peskin also said that the heart was robust. The cells don't have to be perfectly identical. This should still work even if they're not quite identical, as biological systems never would be. But it was, for the math reasons I said, very difficult to prove. Peskin proved it for 2 oscillators. You might sort of chuckle, ha ha, Charlie, you're not so smart. No, come on, it was hard work. Even doing it for 2 was a difficult calculation. He did prove it for 2 with the epsilon, meaning the pulse size, that was small. He was going to use a perturbation theory argument. And then gamma is a measure of the concavity of that curve. Remember I said it's rising but concave down. You might be thinking to yourself, especially if you're a physicist or a mathematician, this whole problem is sort of trivial. Of course they're identical. What else could they do but get in sync? But that's actually the wrong intuition. If the curve were concave up, if it were accelerating up to threshold, they don't have to get in sync. They can get into a weird state where they're alternating like that. One fires, then the other. So the concavity somehow matters to this. And so I proved that with my friend René Marollo for all n, just like Peskin conjectured. So we could prove it in general, and we could prove it was true for almost all initial conditions, which is a technical term that means it doesn't always happen, but it happens with probability 1, if you understand the difference. In other words, there are exceptions, but they don't amount to anything. You would never hit them if you threw a dart at the initial conditions. They're negligible. And under the assumptions that the curve is increasing and concave down. Okay, so I just want to close with a little philosophical rant about this style of math or physics. Why do such a simple problem when we know the heart is nothing like this, the fireflies are not like that? Okay, for one thing, we have this excuse that the real problem is very hard. So we do the simplest problem that we don't understand first. Why is it so hard? Well, the individual oscillators are nonlinear. You can't use all that linear math you learned in school. That's not going to work. You have 2 or more time scales with the slow rise and the fast jumps. You have, the main difficulty was these discontinuities that I mentioned, the impulses, the spikes, the sudden resets. A real problem would have hundreds of variables per oscillator, too high dimensional. You might have noticed, by the way, I didn't quite say, but in the real problem that we did here, sorry, not the real, the model, we assume when one oscillator fires, everybody jumps. So in physics speak, that would be an infinite range interaction or a mean field approximation to the real thing. People have since studied it on networks of various types or lattices, but this was, you always start with the simplest thing, so we did. And the second thing is, and this has been a good lesson in my career, and maybe some of you have had it too. Why do simple models? Because they invite improvement. In other words, it's so obvious what's wrong with what you did that other people will cite your paper. You know, they'll say, and in fact, it's very stimulating to read something that is obviously bogus, because you think, I know, I could do better than that. Good, come do it. Join the party. So this paper has gotten many thousands of citations because it was very provocatively, stimulatingly stupid. Not really, but you know what I mean. That doing a simple thing, you might think you're going to embarrass yourself, and you won't. And the other advantage of a simple thing like this is that it may suggest spin-offs. Like this problem might remind you not of heart cells, but of other things. And it has reminded many people in many disciplines of other things. So just as a quick example, here are some recent citations of this paper. So in cortical networks, in the brain, in wireless sensor networks for people studying electrical engineering, even psychology. There's this field of interpersonal synchronization, people getting in sync emotionally, researchers who study brainwaves of the therapist and the patient during psychiatry, that kind of thing. Nanoelectronics, microscopic machines. Even these days in machine learning, when instead of just gradient descent down to a minimum, there's interest in looking at more complicated learning rules that have more of a neural character, like that last paper, very recent, smooth exact gradient descent learning, but now in spiking neural networks. So I'm out of time. I'm going to keep Nancy off the stage. No, you could come up. All right, I'm done. Thank you very much.
Do we have any questions? Am I on?
You could talk into mine.
Do we have any questions? Pretty soon we'll be.
I have a question, Scott
Hello.
Edwards, evolutionary biology.
Yes.
In the YouTube video, it seemed like the oscillation rate of everything was similar, although not synchronized. I don't know if that's true or not. And I'm just wondering, what's the analogy to the curvature experiment that you showed between that and the original?
Are you suggesting that in the metronome experiment, they were going at the same rate but not in phase with each other, maybe?
Well, perhaps. I don't know. Maybe.
But didn't you hear them all ticking at the same time?
Well, they were started at different times, so they were different. But
Right.
somehow they
somehow got into phase. They really did. They got to not only the same frequency, but the same phase. They were all going, it was 5 of them all going tick at the same time. So now, it's true that the metronomes are not themselves perfectly tuned to you can never make anything perfect. So there would be slight differences in their intrinsic frequencies. And so that may be what are you a musician? See, okay. So, nice. So your ear is better than mine. You probably actually hear that it's a little bit syncopated or something, which I didn't ever notice until you just mentioned it. That's it. I'll have to listen to that now. Okay. I thought they were really in sync, but you're hearing something. So I'm guessing if that's correct, and I have every reason to believe you, then it's because they were not identical in their frequencies. Intrinsically. Yeah. Cool. Interesting.
And next question.
Yes,
Art
please.
Palmer, Columbia University, biophysics. Biological systems, of course, characterized by a lot of feedback mechanisms.
Yes.
And is this jump a kind of feedback, or would that be something completely different in your models?
This is absolutely feedback so what's happening when one oscillator fires, if you want to think of it as an RC circuit, it's been building, the capacitor has built up charge, and then when it fires, it's dumping that charge into the surrounding medium, which is then charging up the neighbors. And so that is a kind of, it's a coupling. I guess that's a substitute word for feedback, I think. Anyway, there's interaction between the oscillators for sure. Without that, they wouldn't synchronize. Now you could ask, what's the interaction for the metronomes? How did that work? So you could see it, right? You saw that as they were ticking, the board that's on top of the soda cans, the board is actually moving sideways. And that puts all the different metronomes into an accelerated reference frame as this thing is moving. And that puts, so to speak, fictitious forces on the metronomes that tends to nudge them in a way that turns out to get them in sync. So it's a cool thing about synchronization that every communication channel that nature has invented is used. It can be done with electricity. It's done in the solar system with gravity. For instance, the man in the moon. You always see the same face of the moon because the moon spins once on its axis for each time it revolves around the Earth. So that spin-orbit coupling is mediated by gravity. And so any force or any way of signaling that there is in nature gets used to bring itself into sync.
That's very interesting. It makes me wonder, these are macro things that you can see. It makes me wonder what might be going on in cells that you can't see, but where that synchronization is a part of the biology.
I'm sure that in developmental biology and other parts of biology that are hard to make, maybe some of our experts here could even point out examples of this. Some colleagues at Rockefeller were showing me some examples in their developing cell systems that they thought there was some kind of like elasticity-mediated synchronization happening through traction forces. I don't know. Anyway, yeah, fun.
Well, good that you didn't go to medical school.
Thank you.
Very much.